All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. How are you guys doing? Thank you for your patience. Thank you for waiting on me. And we're starting class late. I believe there's one other date where we plan to start things late. Just a crazy time. People that I have to be setting up meetings with are on the other side of the globe. And it's just, yeah, it's crazy. So hopefully you guys are all doing well. You had a good weekend. You had a good Halloween. Let's actually jump into it without wasting too much time because we're already starting late. We have a few people trickling in. Let me let them in here. All right, let me share my screen. And okay, let them in. Okay. All right, and I can see the chat. Okay. All right, I think we're good. Another thing, I know some of you couldn't make it to the study hall session that we've had last Friday. I've sent out some messages about it. I posted the video in the same lecture sequence for this class, so you'll see a study hall. I've also sent out an email that I think I'll have like 2 more because it didn't go according to plan. I do think it was some good information, but it was too much to do in one session. So I'm thinking cramming it in 3 sessions probably makes a lot more sense. So last time I presented like an overall kind of strategy, but as you guys probably realize now in Calc 2, the devil is in the details. Kind of understanding what's going on is not good enough because, you know, a question that tugs at certain details, you might get the answers wrong. So I do want to flesh out some things more. So I did schedule another study hall meeting for this Friday at the next most popular time. I also sent out a doodle poll meeting for the following Friday. So if you guys could fill that out, that would be great. It's just to want to combat some issues that students have been facing so far. It's especially disheartening to me that the students who are working hard are still not, well, some of them, right? I mean, in this class, almost half the class has an A. So I don't know, but it's not so widespread among all my classes. So I just want to make sure that everyone is kind of, no, it's not practice problems. In fact, during study hall, I have students from all 3 of the classes I'm teaching. So I'll have pre-calc students in there, I'll have Calc 1 students in there, and I will have Calc 2 students in there. So it's really more of a general thing, just how to go about fitting everything in, how to make sure that when you actually practice something, you're not wasting your time. Every ounce of effort you put in is actually paying off. That sort of thing, just as a general thing. In terms of if you guys are interested in things that are more directly related to Calculus 2 specifically, where you can ask me about concepts of Calculus 2 specifically, maybe go over some problems, maybe go over some overarching general ideas. I think I kind of go over these in lectures as well, but if you still want some sort of summary or some sort of study session, I think towards the end of the semester, I might have those. I might have some extra review classes. Yeah, I don't know. Maybe I might even, well, I don't know. I'll think about that, but that would be something that I would be willing to do in the future. Chances are it would also be on Fridays because that's kind of the only day that I actually have available to move around. Yeah, that being said, let's actually jump into it. So again, I appreciate your patience and your understanding for sticking around with me this late, but let's get into it. So we've been talking about power series. So a power series is just a series that looks like this, and we realize that they expand to look something like this or this, which reminds you of some sort of a polynomial function, but sort of infinite degree. So at first we didn't know if something like that would make sense or what it would mean to make sense, how we would manipulate such an object. So we went through and we proved some things. First of all, these series are absolutely convergent pretty much always. They will always converge. It's just a matter of where. It's possible for them to converge only at one point, in which case, arguably, they're not very useful. I mean, what are you going to do with one single point on a real number line, right? Or they can converge on the entire real line, and then they're a lot more useful. Or they can converge on some interval of finite length that is centered at some point called x naught, the center of the series. The interval on which they converge is called the interval of convergence. And half the length of that interval is called the radius of convergence. If it only converges at one point, we define the radius of convergence to be 0. If it converges on the entire real line, we define the radius of convergence to be infinity. And otherwise, the radius of convergence is just some length that tells you how long the interval is, right? The radius will be half of that, the length of the interval. Okay. Now, whether or not the series will converge at the endpoints is not something that we know off the top of our heads right off the bat. These are things that you have to test for. That just amounts to you plugging in the endpoints into the series and seeing, does the series converge or diverge based on previously learned series convergence techniques. So we went through how to find the radius of convergence and interval of convergence. In Calculus 2, it's always the ratio test. Not in general, but in Calc 2, it's always the ratio test. Every time I ask this question, it's always going to be the ratio test. The only situation in which I can say that you can probably get away without using the ratio test, which I think you could have taken advantage of this on the previous quiz, was if it's a geometric series and you kind of know how those behave already. And we actually used that to our advantage in some examples last time. Right, so when we knew that the function 1 over 1 minus x is what the series n equals 0 to infinity of x to the n converges to, and x is between -1 and 1, non-inclusive. Then, of course, if you have like 1 over 1 minus x over 3, then your x over 3 would be between -1 and 1, so your x would be between -3 and 3. So technically, you wouldn't have to do the ratio test for that. You can just use the fact that you know about the radius of convergence for a very similar series to talk about that one. But in general, if I give you some weird function and ask you to find the radius and interval of convergence, the ratio test is how you're going to go about it, right? So we did some examples of doing that. And in this example, we had the radius of convergence -1 to 1. In this example, the radius of convergence was from 3 to 5, the interval of convergence was from 3 to 5, including 3. And in this one, the radius of convergence was everything. Okay, now we saw that also, where are we? A very important identity. We learned this is true for this particular series. So it turns out that the series here is a geometric series. It converges when our x in absolute value is less than 1. So you can think of your x as the r and your a as 1. And so a over 1 minus r means that, which means this series and that function are interchangeable whenever your x is in that window. Now, that had a lot of useful stuff falling along with it. For one, we could find series for functions that were similar enough to 1 over 1 minus x. So here, if I could actually use algebraic manipulation to make something look like 1 over 1 minus some function, I can actually transform it into a series using that idea. If I had something that was related to something that looks like 1 over 1 minus x via derivatives or integrals, I could find series for those things as well. Now, using that, I could figure out what the series for ln of 3 plus x is. And we actually could plug in a certain value into that. And we found that we could derive the fact that the alternating harmonic converged to minus ln of 2. And so that was pretty neat. Just by exploring power series, we found that, now we have this fancy way that sometimes we can actually evaluate series. which was pretty cool for one. We also did another cool. So that was one of the cool things that we did last time. Of what I think the two very cool things we did last time was. The other one was we actually computed an integral that Symbolab, the powerful Symbolab itself, couldn't actually get a handle on. Wolfram Alpha in this situation was able to handle it in very complicated terms, but we were able to use series to find this integral in relatively simple terms. In fact, this is called a non-closed form. It's an open form because we don't know what exactly this adds up to specifically, even though here we do know that it should add up to some sort of function that can be described here, but you won't always have that. So this is called a non-closed form. However, this happens to be an alternating series, and we know that even though we might not be able to say what that is, we can approximate what that is to any desired degree of accuracy, which is pretty good. And that's useful. I mean, it's not as nice theoretically speaking, but as far as it comes to reality and application, that is more than good enough. If I can find a series and I know exactly how to approximate the result to any desired degree of accuracy, that's just as good or better than having the actual answer. So now we sort of ended with a question. All right, so it's pretty cool that we can use series to do things like evaluate integrals and evaluate series and all that other stuff. And but what if we have a function that it doesn't really fit with 1 over 1 minus x? Like I don't have a way to algebraically manipulate it. There's no connection between derivatives or integrals or any other equation that I could think of. So something like sine of x cubed or e to the minus x squared. How do you express that as 1 over 1 minus x or anything connected to 1 over 1 minus x, whether as an integral or derivative or whatever? Like, how are you going to connect those two to take advantage of that relationship? My ability to write 1 over 1 minus x as a series doesn't seem to help me with these two questions here. So now I ask the question on your behalf. What do we do in a case like this? It turns out that we do have something that we can do. And that leads us into the next section. The next section is going to be a section called Taylor series. Maybe I can make this a little bit, do I want to go bigger? Maybe not that big. Taylor series. So here's where we are. So this is a new topic for today. It's also pretty cool. So the idea is we want a general kind of approach to what we saw last time. So last time, we just noticed, because we know about geometric series, that this series happens to converge to this function, and we can take advantage of that and manipulate it. But what if I don't know that off the bat? I have some random function, and for whatever reason, I want to express it as a power series. The question is, can this be done? And if so, how can this be done? And the answer as to whether or not this can be done is sometimes. Sometimes this can be done. And we are going to look at one of the most famous ways for getting this done. And this is called constructing a Taylor series, or a special case of the Taylor series, which we call the Maclaurin series. So I'm going to pretty much show you what these guys are, how to actually build one, how to actually tell whether or not you can use these guys to do what we did last time, essentially. Okay, so that's the goal for today. At least that's the main goal for today, I would say. And if we have time, I'll talk about some cool applications of Taylor series as well. So that's the overall goal. Given a random function, is there a way to express it as a series? Why would you want to do that? Well, it can make certain calculations easier. For example, we did an integral calculation easier last time, right? So we had the integral of x over 1 plus x to the 9th, right? Which was a crazy thing to do by hand. Possible technically, but there are also cases where we want to be able to do that where technically by hand it's impossible. A series provides a way for us to do this, because the series is really just behaves like a polynomial, right? So when it comes to integrating or differentiating a power series, it's literally just all power rule. It's all power rule. So as long as you can converge absolutely to a power series, that's good. If we can replace a function with a power series, then all my calculus rules now collapse into the power rule. And I can do anything with calculus as easy as it is to do the power rule. Whereas, in general, that's not something that you could actually swing. So that is the motivation for why we want to do this. There's a lot of benefits to being able to use a series to represent a function, use a power series specifically to represent a function. When you go on to future classes, there'll be other kinds of series, like Maclaurin series, Fourier series, things of that sort, where you can express functions as different kinds of series that are very convenient for the situation that you care about. But for now, we just want to be able to express functions as power series. And we're going to sort of take an approach which is very common in a class like differential equations. Right. So when you guys start doing differential equations, you're going to notice that that class is sort of weird in that it's a class that's very hopeful about you're always trying to pretend that the answer is out there. And you might even pretend that the answer has a certain form. And then you go out and look for the answer of that certain form. And then it turns out mathematically in hindsight that was the only answer that was actually out there, which is pretty useful. But I'll let you wait until differential equations for something like that. So that's what we're going to do. Let's pretend that we could actually do this and then try to figure out in hindsight, what would it have taken for us to be able to do it? And so let's pretend there is a way. So that's what I'm doing here. Suppose we can. Right, so that's what I'm highlighting there. Suppose we could write f of x equals some power series. How would that power series have to behave? Well, the x minus x naught to the n, that's common for all power series. A power series is going to be distinguished by its coefficients, right? What are these numbers cn's that are going to work for this random function that I picked, right? So we need a way to figure out the coefficients, right? So observe grasshoppers. How would we go about figuring out how to actually find these guys? Well, suppose, so we're assuming that, our f of x can be written as some power series centered at x naught. So f of x can be written as c0 plus c1 x minus x naught plus c2 x minus x naught squared plus c3 x minus x naught cubed plus c4 x minus x naught to the fourth plus dot, 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 right? So we just pretend that we can do this. What would have to occur for us to be able to do this? More specifically, what are the c values that would have to be there in order for this to work out? It turns out, and you may or may not notice this right away, is that there is a way that we can actually isolate one of the c values in this function and figure it out. And this is c0. Does anyone see any way for us to figure out what c0 is? And you might even remember a technique like when we were doing partial fractions. Remember the arbitrary coefficients that we needed to find? We had this random equation where there was a function on one side and there was the stuffs with a and b and c on the other side. What were some ideas? What were some ways that we could actually figure out what those things were? Ideas?
If you were given an equation for f of x, couldn't you put 0 in for x?
Well, putting in 0 for x wouldn't help us find the c's, right? Because if I plug in 0, I would have f of 0 on the left side. And then on the right side, I would have c naught plus C1 times minus x naught plus C2 times x naught squared plus C2. I'd still have an infinite series. I wouldn't be able to isolate anyone like that. But you're thinking along the right lines, actually. Just refine that approach. The answer is to plug in something. But what is the thing you would plug in?
Would it be x equals x naught?
Okay, so here's the low-hanging fruit. Notice that if I plug in x naught on the left side, what's going to happen on the right side? Well, x minus x naught, all of those guys are going to go to 0, right? So all of these guys would go to 0. Right? And I would actually have isolated the C0. So in other words, I would be able to say, well, my C0 is f of x naught. Right? So now I have one coefficient down, an infinite number of coefficients to go. One bottle of beer on the wall, we knocked one down. Infinite Aleph naught bottles of beer left on the wall. Okay, so let's actually find the others. So here's actually a trick. We're in a calculus class. So here's something that could be done. I could find the derivative. Now you might want to think, well, why would you find derivatives? Well, for one, C naught is a constant. So if I find the derivative with respect to x, the C naught's going to disappear, which is fine because I already know what that guy is. But also now what's going to happen is that I would be left with C1 as the second term. Then I would have 2C2 x minus x naught plus 3C3 x minus x naught squared plus 4C4 x minus x naught cubed plus 5C5 x minus x naught to the fourth plus dot, dot, dot. Any ideas for what to do now?
Plug in x naught.
Plug in x equals x naught again. It worked out last time. So now if I plug in x naught into the derivative, I would get, well, C1. In other words, I now know that my C1 is f prime of x naught. So now you might be wondering, well, is that it? My Ci is just the ith derivative evaluated at x naught. Well, not so fast, right? You don't want to just make a whole pattern off of just two guys. Very risky, right? Something like that can make you think that all odd numbers are prime after you just checked 3 and 5, right? You don't want to end up in that situation. So what we can do is keep going, right? The strategy seems to be working so far. So let's keep going. Second derivative. Notice now that this will be 2C2 plus 3 times 2C3 plus 4 times 3C4 plus 5 times 4C5 and again, let's do that. Let's plug in x naught. This is going to give me, well, 2C2. So now it looks like something is breaking the pattern. So our C2 is actually the second derivative at x naught divided by 2. Okay, so is it Ci is the ith derivative at x naught over I? Let's actually do one more. Or maybe two more, who knows? So here I would have 3 times 2 C3 plus 4 times 3 times 2 C4 x minus x naught plus 5 times 4 times 3 C5 x minus x naught squared plus 6 times 5 times 4 C6 x minus x naught cubed plus dot dot dot. Here, if I plug in f triple prime at x naught, I would get 3 times 2 C3. This means that my C3 is f triple prime at x naught over 3 times 2. And I wrote that as 3 times 2 because I want to see you, hopefully you guys are seeing a pattern here. Let's do one more. F to the fourth derivative. This would be 4 times 3 times 2 C4 plus 5 times 4 times 3 times 2 C5 plus 6 times 5 times 4 times 3 C6. This means that f to the fourth derivative at x naught is going to be equal to 4 times 3 times 2 C4, which means that my C4 is going to be f to the fourth derivative evaluated at x naught over 4 times 3 times 2 times, well, times 2. Okay, so now dot, dot, dot. Can you guys see a pattern? Like if I were to ask you, what is Cn? Yeah.
F to the n of x naught over n factorial.
F to the n of x naught over n factorial. Notice that what this guy is, and we have to make sure that pattern works for everyone. I can think of this guy as, well, f to the 0th derivative at x naught over 0 factorial. Here, this is f to the first derivative at x naught over 1 factorial. Here, this is f to the second derivative at x naught over 2 factorial. Here, this is f to the third derivative at x naught over 3 factorial. Here, this is f to the fourth derivative at x naught over 4 factorial. And the pattern would continue. At this point, as a Calc 2 student, you probably won't be able to prove this in general. You'd use something like induction. But at this point, it should be clear what the pattern is, and we can even see it coming right up. This here is going to give you a 5 factorial. After 2 derivatives, this is going to give you a 6 factorial, etc. You can see the pattern is coming up again. So it turns out that if I were to pretend that my function is can be represented as a power series, the coefficients would behave in this way. And so we'd guess that f of x, we can write it to look like something like this. Now, as it turns out, this is a pretty good guess, and it turns out it's actually useful and true in a lot of cases. It turns out, though, unfortunately, turns out this is not always the case. It turns out the right side may not exist or be equal to something else, etc. We'll talk about more on this later. But that would be a good guess, right? if I want to be able to express any function as a power series, this is a nice guess. This is what's called the Taylor series, okay? So this is a way to write f of x as a series. That's called the Taylor series, named after the mathematician Taylor. It turns out that if you call the point that you center around is x equals 0 specifically, then we call it a Maclaurin series. In other words, a Maclaurin series is just a Taylor series centered at 0. Okay. Now, it's very important that you realize that our ability to do this comes with certain caveats, right? So one, in order to even construct this guy, our function must be infinitely differentiable. Notice that I have to be able to find the nth derivative, and n is going off to infinity. I have to be able to find the first, the second, the third, the fourth, the fifth, the sixth, the seventh, forever, right? I have to be able to infinitely differentiate some function. So that's the first thing. Second thing is, and this is something I'll make a little bit more precise, and I mean, it's Calc 2, so it's not going to be ultimately precise, but I'll make it a little bit more precise. The magnitude of the derivative must not get too big. The derivatives have to behave themselves. They can't get out of control. What do I mean too big? Well, so big that this power series would diverge in the ratio test for all points except x naught, for example, right? So we know that a power series will always converge. This will converge at minimum for x equals x naught. Right? But it's possible that if my x is not x naught, so this part is non-zero, that the coefficient part gets so big that when I do the ratio test, I get a limit that's greater than 1. So I don't want that, right? So the derivatives have to be controllable. They have to not grow too big too fast, okay? So given a function, if I can find, if I can infinitely differentiate that function on some interval, and the derivatives don't get too big on that interval, then it turns out this might be a way to write that function as a power series. Okay, and this leads us to the definition of a Taylor series. Very, very important definition. So you definitely want to have this memorized. Right? So the Taylor series for a function is this series. That's the Taylor series centered at x equals x naught. If I plug in x naught equals 0 specifically, I get a series that looks like this, and that is called the Maclaurin series. It's named after another mathematician. I also want you to notice that I took great care in this box not to write f of x equals this. I just wrote down if f of x is a function and such a series exists, this one is called the Taylor series for the function. This one is called the Maclaurin series for the function. It might not be equal to the original function. We'll talk about that in a little bit, but it would be a pretty good guess. If I were to guess a power series that would be equal to the function that I'm looking at, this would be the series that I would guess. Okay, so that's called a Taylor series. Okay. So notice that I did not say f of x equals that. That was intentional. We are going to see situations where f of x is actually equal to this guy. We'll talk about that, what the implications are, what we can do with them. But in the meantime, let's actually do some examples. So here are 3 functions that I don't see any nice way to connect to 1 over 1 minus x, but we're going to find power series to represent these functions. In fact, I'm going to find Maclaurin series specifically. So let's actually find the Maclaurin series for these guys, which is just the Taylor series centered at 0. So let's move this over here. Okay. So let's say my function is f of x equals e to the x. How would I go about constructing a Taylor series centered at 0 for this function? Also, let's find the radius of convergence and the interval of convergence. So what do we do? Well, I know that the coefficients are going to be given by, well, it's a Maclaurin series, so it's going to be given by this guy right here. That's how I'm going to find the coefficients. So I need to be able to describe the nth derivative evaluated at 0. That's the goal. So here, of course, the 0th derivative is just e to the x. This means that if I evaluate that at 0, the answer is, well, 1. right? E to the 0 is 1. If I take the first derivative, that's e to the x. Evaluate the first derivative at 0, and it's 1. Okay, second derivative. That happens to be e to the x. Evaluate the second derivative at 0, and you get 1. Very exciting. Okay, I know the second one is going to be a surprise, but the third derivative evaluated at 0, also 1. I guess we see where this is going. Do we need to do more examples? I don't know. What do you think the nth derivative evaluated at 0 for this function is?
1.
It's 1. It's always 1. So it turns out that that is going to be, so this means the Taylor Maclaurin series for f of x equals e to the x is, well, it's the series n goes to from 0 to infinity of f to the nth derivative evaluated at 0, but that's just 1, over n factorial times x to the n. Or in other words, that's equal to x to the n over n factorial. That's the Maclaurin series for e to the x. Now, we saw this guy before. Now, you might not remember, it's probably been a while, but we did see him last week. Where did we see this guy? Power series. There he is. X to the n over n factorial. I kind of snuck him into a previous example. We already found the radius of convergence and interval of convergence. It actually converged everywhere, absolutely, right? So, yeah. So we actually know that the radius of convergence is infinite, and the interval of convergence is the entire real line. So the function f of x equals e to the x has a Maclaurin series. That Maclaurin series actually works on the entire real line. Now, whether or not that series can actually represent e to the x is a whole other story, but it turns out that it does. This is something that we'll justify a little bit later. But it turns out in this case that e to the x can be thought of as equal to this guy. We'll talk about that a little bit more. Let's do another example first, though. Let's look at cosine. Let's see, if I wanted to write cosine as a series, how would I go about that? As a Maclaurin series. So again, you play the same game. You just want to find a way to write the nth derivative evaluated at 0 in this case, because it's a Maclaurin series. So of course, the 0th derivative is the original function. So if I evaluate that at 0, well, that's 1. Cosine of 0 is 1. The first derivative is going to be minus sine x. Evaluate that at 0, get 0. Sine of 0 is 0. The second derivative is minus cosine x. Evaluate the second derivative at 0, you get minus 1. Third derivative is, well, positive sine x. Evaluate the third derivative at 0, you get 0. The fourth derivative is cosine. And of course, if you evaluate the fourth derivative at 0, you get 1. Now notice from here, you're right back where you started. You started with a cosine and now you're back at a cosine. So the pattern is just going to repeat. So now you're in a situation where this pattern repeats. So you're going to have a 1, then a 0, then a -1, then a 0, then a 1, then a 0, then a -1, then a 0, then a 1, then a 0, then a -1, then a 0. You're going to start to notice things. So for example, if you look at this very closely, very hard, you look at it for a long time, you basically end up noticing the following is going to happen, right? So here's a pattern. If n is odd, f to the n of 0 is 0. So this probably tells you that when it comes to a series, we can probably ignore the odd terms. Okay, every time I hit an odd derivative, evaluating it gives me 0. So it's like I have this series where I'm adding this plus 0 plus this plus 0 plus this plus 0 plus this plus 0. Might as well you don't even just ignore the zeros. Why are you just adding zeros intermittently all the time? Now, you don't have to ignore it, but to write it down efficiently in the way that I want to write it down, I'm going to choose to ignore it. Also, what you're going to notice, if n is even, then your f to the n of 0 is pretty much going to be equal to plus or minus 1. Now, there's a way that you can actually say this. So let's say, for example, your n is even. Say you can write n as 2 times k for some integer k. Then you would be able to say, well, this is plus or minus 1, which means it's just alternating sign, goes from +1 to -1 to +1 to -1 to +1. And what happens is you can actually track this by the value of k. So for example, I know that when k equals 0, I want to get a +1. When k equals 1, which means my n is going to be 2, I want to get a -1. When k equals 2, my n would be 4 because it's 2 times k, so that would give me a +1. So essentially, you can just let it be k as the power. And ultimately now, you see this leads to the following. The Maclaurin series for f of x equals cosine of x is, well, it's going to be the series, n goes from 0 to infinity. You're going to have -1 to the n, and then you're going to have x to the 2n over 2n factorial. This just guarantees that I only have the even numbers, right? So it's like here, I wrote it as 2k and then just make the -1 to the k. But of course, k is a dummy variable. Can replace k with n since it is a dummy variable. Right, we did something like that already. Okay, so I just rewrite n as a k just to see how the pattern can unfold, how I can take advantage of it. But then when I plug everything back in, I can just use n's everywhere instead of k's, and it's not going to matter. So that would leave me with that. So instead of n factorial in the denominator, I would have 2k factorial. And instead of x to the n, I would have x to the 2k. And then I would have -1 to the k. But then I can just go everywhere and replace the k's with n's. It's not going to make any difference. Okay. And so we are going to have this guy being the Maclaurin series. And it turns out, of course, cosine and sine are very similar, right? You start taking their derivatives, they just, again, they kind of go in this loop. This is similar to the last example. Verify the following on your own. So go home, try this once. You only have to try it once. Make sure you can get to it once. And then from now on, you're going to just know that. Verify the following at home, which luckily for you guys, you're already at home. That's great. That the Maclaurin series for sine is the following. It's going to behave similar to cosine, except where the cosine gave you ones plus or minus one on the even terms, the sine is going to give you plus or minus one on the odd terms. So this guy is going to give you x to the 2n plus 1, which is a generic way to write an odd integer when n is an integer, over 2n plus 1 factorial. Now, here's a pretty cool connection that you're probably haven't thought of. But remember when you studied even and odd functions in Calc 1? And we saw that, okay, an odd function is one where it's symmetric about the origin. So if I take the right side, I flip it in the y-axis, then flip it in the x-axis, I get the left side. We also know that the integral from 0 to a is equal to the negative of the integral from minus a to 0. And we learned a bunch of things about odd functions. And it was weird. Well, we kind of knew why we called it an odd function. So our quintessential example in our head was x squared and x cubed. But you also would have learned that sine of x is an example of an odd function from Calc 1. Actually, you actually knew that since pre-calc, by the way, also. You also learned that cosine of x was an even function. And now look at this. If I describe cosine of x as a power series, it will only have the even powers. Notice that if I were to write this out, it would look like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. This function that we called odd back in Calc 1 happens to only express odd powers of x. That we called even in Calc 1 only expresses even powers of x, while a function that we knew as odd in Calc 1, if you were to write this out, he only expresses the odd powers of x. Pretty neat, very poetic. This is in fact true. If you have an even or odd function in terms of how you learned it in Calc 1 or geometrically, you can know that if I can write that as a power series, the powers are only going to be the even or odd ones. A function that is neither even or odd will have other powers of x other than even or odd. So that's actually pretty cool. You can actually tell if a function is even or odd based on what its power series would look like if it has one. So I thought that was a pretty cool poetic little tidbit right there. It's pretty neat. Okay, so actually try to verify this. Just copy my example from above. Make sure you can actually go through the motions and know how to do that. You definitely want to make sure you can do that. Okay. So that was sine of x. So here I computed the Maclaurin series for e to the x, cosine of x, and sine of x. It can also be shown that the Maclaurin series of cosine x and sine x have radius of convergence infinity, and interval of convergence is negative infinity to infinity. For example, for cosine, for the Maclaurin series of cosine. So this is going to be the guy minus 1 to the n, x to the 2n over 2n factorial. By ratio test, you would set the limit of, you can ignore the minus 1 to the n, so it's x to the 2n plus 2 over 2n plus 2 factorial times 2n factorial over x to the 2n. This is going to be the limit of x squared divided by, the 2n factorial is going to kill everything after, so you're going to have 2n plus 1, 2n plus 2, 2n plus 1, 2n factorial, and then that cancels, so you'll have that. Now, this is the limit as n is approaching infinity, so your x you can think of as a constant here. So here you have the denominator growing off to infinity while the numerator is staying fixed. That approaches 0. And of course, that's less than 1 always. So radius of convergence equals infinity. Interval of convergence equals negative infinity to infinity. A similar thing happens for sine x. Try it. Okay, so make sure you try that. Okay. Now, this is something that this leads to the following. Yeah. Gave myself a lot of space here. Still more space. No, it's a little too close. Okay, so what I just showed you was the following. Well, ultimately the following. In row 1, we actually saw that last week, right? So if we have a function here, a Maclaurin series for that function can be, for 1 over 1 minus x, it's the series from 0 to infinity of x to the n. That guy has radius of convergence 1, interval of convergence minus 1 to 1. For e to the x, cosine of x, and sine x, I just showed you how to find all these Maclaurin series. And we saw that the radius of convergence is infinity and the interval of convergence is negative infinity to infinity. Now, this very important table. memorize. It's one of those things, kind of like just, well, any form that keeps showing up. Knowing the Maclaurin series for these functions, very important. They will show up when you least expect it to. And at any given time, you should be able to think of these guys as interchangeable with their series. And this is now true from now until forever. Forever in mathematics from now on. Whenever you see any of these functions, you should immediately be thinking of their power series representations. It's going to be relevant for the rest of your mathematical careers. And you never know when it's going to be useful. It is also very useful to know that these guys are actually equal. So it's right here, and we'll justify later. So as I mentioned earlier, just because you can find a Taylor series does not mean that it's actually useful or representative, or it actually converges to the function, or it can be interchanged with the function. However, these particular functions, these particular series, that is true. So you should know these by heart. And now it's just another way you can think of these functions. You think of it as the same identity. In the same way you know that 1/2 is the same as 0.5, it's the same as 4/8, it's the same as 2.5/5. There are so many different ways to think of the number 1/2. You have equivalent representations that might look different, but you know that they're all really the same. In the same way, now you know this. A series, these series are just alternative representations for these functions on these intervals, right? So just as how there's no difference between 0.5 and 1/2, they're literally the same thing. They're written differently. In that same way, these functions are literally the same as these series. In every situation where we use these functions, we could have used the series. You can literally go back in history, back in time, Calc 1, pre-calculus, everything. And if you were to replace, every time you saw one of these functions, if you were to replace that function with the series, just everywhere you saw a sine of x, just erase it and write in this series, in all your notes going back, nothing would change. Like everything that was said is still true. Literally nothing would change. Like everything would be exactly the same. It's like you're going back through your life and every time you wrote 1/2, you now replaced it with 0.5. No difference. It's not going to change anything at all. Like it's literally one and the same. Different ways to write the same thing, right? Which is actually a super important and very useful thing. As we saw, well, we actually saw an application of that earlier, where we had a very tough integral, but we can write the function as a series and then the integral isn't so tough anymore. This is useful in the same sort of way and in more ways, believe it or not. So that's going to be very useful. So yeah, so this means we're allowed to write the following. This equals that. And of course, there's a caveat here if your x is between -1 and 1, right? This equals that for all x in R. Same thing here. This equals that for all x in R. So no matter where you are on the real line, you can replace sine of x with these guys and no one would notice the difference. If you're on this interval, you can replace the function 1/1 minus x with that series and no one would know the difference on that interval. Outside of that interval, someone's going to notice, hey, that's not the same, right? Because that actually, the right side diverges outside of that interval while the left side is still a thing. So yeah, you're allowed to write equality, right? And these guys, we can think of these functions and their Maclaurin series as one and the same very important idea to wrap your mind around. And literally everything that was true before is still true now. I figured I would show you a nice little example that's not super trivial, but maybe it's like a calculus example. Let's find the derivative of sine of x, right? So we know that the derivative of sine of x is cosine of x. And if you went back to Calc 1, you would have proved this at some point. You would have used in the proof, oh, the limit as h approaches 0 of sine h over h is approaching 1. And you can use a trig proof for this by using the limit definition. Let me show you another proof for this. I can actually literally replace the sine of x with this series. And I'm telling you, it's not going to make a difference. Well, this is just an infinite polynomial. And I know that this series converges absolutely on the entire real line, which means I can switch the series and the derivative because of absolute convergence. And this is the derivative with respect to x. So whenever I see an n, it's just a number. So my focus when I'm taking this derivative, it's just going to be differentiating that. And I'm going to leave everyone else the same. So that's going to be minus 1 to the n times 2n plus 1, subtract 1 from the power. So of course, you're going to notice this is going to cancel into that, and I'm going to be left with 2n factorial left over. And look at that. What's that guy? That's cosine, right? And some people might even like the proof of the derivative here a lot more than the one you did in Calc 1. I didn't have to remember any trig formulas. All I had to remember was how to differentiate a polynomial, which everyone remembers that, right? The derivative of x to the n is n x to the n minus 1. Not everyone remembers their special trig limits, even though they should. The limit as x approaches 0 of sine x over x is 1. The limit as x approaches 0 if x minus cosine x over 1 minus cosine x over x is 0, and limit as x approaches 0 of tangent x over x is 1, right? So yeah, literally one and the same. Everywhere you have done anything with any one of these functions at any point in time, you can actually swap them out with their series. It's not going to make a difference. So that's pretty cool. It's also pretty useful, as we will see later on. So that's the idea of a Taylor series. Now, you can pretty much ignore this because I don't think I'd ever really ask that. But some students asked, what would the Maclaurin series for a tangent function look like? And you can construct this in several ways. And I posted a bunch of links here that talks about that. So you can actually divide one series by the other using polynomial long division. You can construct it from scratch by taking derivatives and plugging in convenient values, etc. So there are a bunch of different ways to find the Maclaurin series for tangent. You won't have to know that or memorize that though. But I have had that question asked a couple times, so I decided to put some resources on it. That's the idea of a Taylor series, and this is something we'll justify later. But you can actually think of certain functions as their Taylor series. And for these functions in particular, it is very convenient, very useful. Any questions on Taylor series? So far, anything I mentioned?
No, I think we're good.
Okay, awesome. All right, moving on. let's start talking about some applications of Taylor series. What is it good for? Okay, so I'm going to run through like 5 applications here, but really you only need to know really one of them. So we'll get to that. And the application that I expect you to know at minimum is using these ideas to evaluate integrals, similar to how we did last class, right? So that's going to be a very important application, and I'll do some more examples of that. But I also wanted to touch on some other applications of Taylor series because just in general, I think there are things that you should know, and otherwise they're actually pretty cool. So I will actually spend not a lot of time, but a fair amount of time on this one. Very cool / useful. Because this is a weird one. It's very rarely talked about in Calculus 2, but when you go to higher classes, and I'm thinking specifically of a class like differential equations or complex analysis, people are just going to randomly expect you to know this out of nowhere. It just reminds me of schools where they don't talk about complex numbers at all, but eventually you go into a class where now the professor, oh, complex numbers, blah, 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 and they start doing it on the board. It's like, no one told us what a complex number even is. Like, we're not allowed to use complex numbers. But yeah, so Euler's equation, very, very important equation, very, very useful equation, very, very beautiful equation. I'll talk about that a little bit. And it's something that there's going to come a point in your mathematical career, if you go high enough, where you're just going to be expected to know, at the very least in differential equations. And when it comes to differential equations, if you're a math major, you need to do differential equations. Whether or not it's prescribed for your major, doesn't matter. You must do differential equations. Can't be a math person and not know about differential equations. You cannot be a physics person and not know about differential equations, right? So math and physics, definitely, you need to know differential equations. Engineering, can't be an engineer and not know about differential equations. So if you're interested in engineering, you need to know about differential equations. Chemistry, I would say it's not completely necessary, but it would be to your benefit. Like if you're a chemist and you don't know you've never seen it, you don't know anything about differential equations, I wouldn't fault you, but you would be a better chemist if you knew differential equations. Biology people, I think for the most part, you can get away without it, for the most part. But if you're in one of the more technical sciences, differential equations, you need to know it. And Euler's equation comes up there, as well as a series would come up there as well. And a lot more series than Taylor series. So like a Fourier series is something you'd learn about in differential equations usually, which has an idea, kind of a similar flavor to a Taylor series, except it's not an infinite polynomial. It's like an infinite series of sines and cosines. I will let you worry about those when you get to them. So I'll spend a little bit of time on application 1. I will rush through applications 2, 3, and 4, and then we'll spend a little bit of time on application 5 by going through some specific examples here. So I'm going to kind of talk about this in general, go through a specific example here, rush through the other ones. And because I already showed you similar examples to application 5, not going to take forever on that either, but it's very important. So you need to know that. So first one, very cool, very useful, won't test you on this though, unless maybe a bonus problem or something. Just so you know. The others are just for your education. Okay, so, all right, let's actually jump in. Good old Euler, the mathematician Euler. One of the few mathematicians of antiquity. Not only is he very respected, very revered, thought of as a demigod in the mathematics community, but he's one of the few mathematicians who was very prolific even until his old age, which of the classical mathematicians, that's actually pretty strange, statistically speaking. in modern times, it's very normal for math people to be consistently contributing to the field many years into their career. But in antiquity, this was not the case. Most mathematicians, they would actually make their contributions at a very young age, and you won't hear much from them afterwards, or at least not in as much glory. A lot of the most advanced mathematics we're studying these days was invented by kids, teenagers, and people in their low 20s, believe it or not. However, Euler was prolific. He came up with many theorems, many things in mathematics. The number E is named after Euler. So many things are named after Euler, to the point where at this point, if you go high enough in mathematics and you want to say something like Euler's theorem or Euler's formula, you'd have to specify which one, because he's all over the place. Okay, now, when it comes to complex numbers, not a detailed course description here, but there is something called the imaginary unit. This is a number we called I. This is a number such that when I square it, it equals -1. So I is the solution to an equation like x squared plus 1 equals 0. Now, there is no real number that would solve this, so we made up a number that we say would solve this. We call it the imaginary unit. And you might be like, well, are you just allowed to do that, make up your own answer? Yes. I'll let you grapple with that with your complex analysis professor, because we'd go too much in math philosophy. Why is that allowed? Is that even math anymore? Now it's just magic. You're throwing in imaginary stuff. But let's assume for the sake of argument that I could construct a number so that when I square it, I get -1. What would that mean? Well, that would mean that the number is the square root of -1, which means if I square it, I get -1. Which means if I cube it, I would get -I, because it would just be I squared times I. If I raise to the fourth, I would get +1, because it would be -I times I, which is -I squared, which is -1 times -1, etc. I to the fifth would be I, and then pattern repeats, right? Kind of like how sine and cosine repeat. But almost exactly like how sine and cosine repeats, actually. You'll notice that it repeats up to the fourth step. There's something, there's a nice message hidden in here. By the way, there is a kind of number and a kind of function that's going to come up strangely often in a class like complex analysis or differential equations. It's going to be connected to circles and how you think of the real plane and polar coordinates and a whole bunch of things, which we'll talk about polar coordinates in a little bit. But that is this function, e to the I times x, which seems like a very curious thing to need to know about. But believe me, it's going to come up a lot. It's a very important kind of function. So now let's actually look at this function. We know, well, now we know as of like 15, 20 minutes ago, that e to the x can be thought of as this guy. Right, which you're going to have memorized. Does that on the entire real line. Now let's actually assume this extends, right? So this would mean our e to the I times x, well, that's going to be I times x to the n over n factorial. Okay, what is that? This is just going to be I to the n, x to the n over n factorial. This is going to be, now let's actually just plug in the n's and write these out. Okay, so n equals 0, you would just get 1. N equals 1, you would get ix, right? You just get ix actually. N equals 2, you would get I squared x squared over 2 factorial. N equals 3, you get I cubed x cubed over 3 factorial. N equals 4, you get I fourth x to the fourth over 4 factorial. N equals 5, you get I to the fifth x to the fifth over 5 factorial plus ... Now, let me write one more. You get I to the 6 x to the 6 over 6 factorial plus ... Now, I can actually use this equation up here, call this equation, or equations 1 then by equation 1, I'd be able to write these out. So I is just I, sure. I squared, though, is -1. I cubed, right? That's going to be minus I. I to the 4th is going to be +1. I to the 5th, don't have this, is going to be I. So that's going to be plus I. I to the 6th is going to be +1, etc. Now notice that I can group all the guys with I's, group all the guys without I's. Guys without I's, well, it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. I to the 6, that's actually I squared, which is -1. So this is actually a minus here. It's going to be minus x to the 6 over 6 factorial plus ... All the guys that have i's, well, there's an x. There's a minus x cubed over 3 factorial. There's a plus x to the 5th over 5 factorial. There would be a minus x to the 7th over 7 factorial plus ... Anyone notice anything?
The left looks like cosine and the right looks like sine.
That not only looks like cosine, the left is cosine. It is cosine, exactly. And the right is sine. So this means that e to the ix is equal to that. Now, because we often think of these as angles, this leads to what we call Euler's equation. Now, because the x is often thought of as an angle because you're plugging into sines and cosine, sometimes it's written as this with a theta in it. Now, here's something really cool. Plug in theta equals pi. So here, you would end up with e to the I pi is going to be cosine of pi plus I times sine of pi. Sine of pi is 0, and cosine of pi is -1. So it turns out that e to the I pi is -1, or that is true, which 1 is very weird, but 2 is also very beautiful, very interesting, that we can actually take a real number, put a complex number in the power, and the output is also a real number. On top of that, if you rearrange this equation and write it in this form, like I wrote here in the box, you will notice that pretty much every important quintessential mathematical constant is present in this equation. It's a very short equation that has 1, all the important mathematical constants, e, pi, I, 1, 0. It has all the important mathematical operations. Multiplication, because you have the I times pi. Exponentiation, you have the I pi in the exponent. You have addition with a +1. You have equality with the equal. So you have e, which comes from e to the x, the most important function of all of mathematics. You have the mysterious I, the enigmatic pi. You have the multiplicative identity for the real numbers 1. You have the additive identity for the real numbers 0. You have all the important mathematical operations all in one short equation. People geek out over this equation a lot. And even if you go to this YouTube video here, you'll see a very good mathematician, Po Sheng Lo, geeking out over this equation. It's one of those things that people find a lot of beauty in, and I even wrote a little paragraph there commemorating its exceptionalness. It's a very, very, it's considered by many to be one of the most beautiful equations in all of mathematics. You talk to a lot of math people or math enthusiasts and ask them to list their favorite equations or their favorite identities. This will be in the top 5 of pretty much anyone, for sure. And it'll be number 1 for a lot of people. Very interesting thing. But it turns out, so not only is it interesting because it's beautiful, but this equation itself is so useful, it is not even funny. There are so many things that we know of that we can prove, that we can think of things in easier ways just because this particular equation is true. We can create a linear combination of sines and cosines and write that as an exponential. You'll also notice that the cosine tracks the x-coordinate on a circle and the sine tracks the y-coordinate on a circle. So if you were to draw like the plane where the real axis is here and the imaginary axis is here, then any coordinate in the plane, a comma b, can be thought of as equivalent to some complex number. And so you have like this exponential form of any complex number. And you can match that immediately with a circle that's connected at the angle. So it's like a brilliant combination of mathematics and geometry all in one nice little compact flavor. It's really amazing and it's really useful. It's not even funny. I don't know, maybe I should have left that up. So it's the amount of things that come out of this equation, it's mind-boggling, right? A very, very important equation. And I was also going to show you guys. Yeah, maybe I'll talk about the binomial theorem next time. Let me skip over this for now. I throw this in there not because I expect you guys to know about it really, but it is a cool application of Taylor series. And it's something that I keep telling my students since algebra. You can't distribute a radical across the sum. And I tell my Calc 1 students the same thing. You can't distribute a radical across the sum. And I kept telling them, well, if you could, you would actually distribute it into an infinite number of terms. And if you want to know why that's true or how you would actually do that or how you'd actually compute that infinite number of terms, it turns out Taylor series is the way you would actually do it. And so I'll actually show you how to expand a radical. Well, I'll just talk about it. How you'd expand a radical as an infinite number of terms. And I'd be able to show you that the radical of 1 plus x is actually equal to that guy, believe it or not. And so when a lot of students will see something like this and write 1 plus x, it's so wrong, it's not even funny. If you wanted to express it in 2 terms, 1 plus x squared over 2 is actually a better approximation. And we know that because of Taylor series. So you can actually talk about distributing radicals and how you'd actually do that. You'll always get an infinite number of terms, and we know this by Taylor series. You can also compute limits. So you see something like this here. I can replace sine of x with its Taylor series. It will neatly cancel the x's, and I would be able to actually get that limit pretty quickly. So notice here, if you were to do this another way, L'Hopital's rule would be probably something that you would try. You'd have to do it like 3 times for it to work. So instead of that, if you just saw sine as its power series, you can actually get it without the need for L'Hopital's rule, no calculus necessary. You can literally just plug in the number and solve for the limits. I would encourage you to actually try it here. Again, I might not ask you to do this, may ask as a bonus, but probably not. So if you want extra points, it's a really cool application, a computational application of Taylor series. And yeah, it's another way to compute limits. And chances are, if you're plugging a limit into your calculator doing L'Hopital's rule, it's going to think of it as a series and do a lot of limits behind the scenes. Being able to write constants as infinite series, also a very useful application. So knowing that e to the x can be this, it means that, for example, I can think of e as e to the 1, which is this. So I can write e as an infinite series of things. It also tells you that e is 2 point something. You can write arctangent as an infinite series here. You can therefore express pi as an infinite series of things, and you'd realize here that pi is actually something that's less than 4. We know that it's 3.14159, etc. So you can actually do that. And this is a very number theoretic example, but you can actually prove a lot of important things by expressing certain numbers as this infinite expanded form, and you can actually use that to your advantage. So a lot of times you'll see things like this where people expand pi and other things in these weird ways. Like, first of all, how do you know that? And second of all, why is it useful? Well, Taylor series is one way that people would know how to do this, and it's actually useful in a variety of proofs. In a lot of math theories, you can figure out a lot of things. So we can do all this mumbo jumbo, switching things out with series, and we can figure a lot of things out. This is the important application, though, and I'm actually going to wrap up here, but actually using it to evaluate difficult or integrals that it's literally impossible for you to evaluate by hand. So very important application. We'll test you on this. So the idea is just like the idea that we had in the last class. I can give you a function, and it's very complicated to deal with by hand, maybe even impossible to deal with by hand, literally impossible to find an antiderivative. And what you can do is you can replace that function with a series and then just do the integration with the series. That's the application that I want to show you here. So last time we had the integral of x over 1 plus x to the 9th. We transferred it into a series, we could integrate it, and then we could actually approximate the definite integral. We're going to do the same thing here, but now we're going to do it with functions that aren't really connected to sine to 1 over 1 minus x. Things like the sine function or an e to the minus x squared, things that don't really look like a 1 over 1 minus x. We can now, because we know about their Maclaurin series and their power series, we can actually get series into the mix for these guys here. So I highly recommend that you try these because it is something I'm going to test you on. So I'd rather you try it before I do the answers for you next class. And yeah, I'm going to actually, again, use Euler's formula to derive some things about hyperbolic functions. Derive these guys. So you guys can also try that. It would be good practice. And so that's the thing with series. And I think I mentioned this in an email. Series really isn't hard, all things considered. It's just very strange to students for a long time. And just the unfamiliarity breeds this kind of anxiety that just confuses everybody on it. The way to get over that is to just do a lot of practice. So I'm going to wrap up here, but I do want you to practice at least this example. Maybe go through and try to derive these formulas for Thursday's class. Also, make sure you can find the Taylor series for sine function. You can derive it from scratch. Make sure you know how to find the radius and interval of convergence for the sine function, sine functions Maclaurin series. Find Maclaurin series for other functions as well. If I were to ask you, the function is x cubed. Find a Maclaurin series centered around 1. Could you do that? Try it. And just do some practice and actually try that. So I'll leave these guys in the notes for you to mull over and actually try for next time. Please actually do try it. You don't want to get in the situation, get behind on series, because just the sheer unfamiliarity of it will make studying it harder. So you need to get as familiar as you can as soon as possible. So we'll wrap up there. I'll talk a little bit about binomial theorem next time, as well as do more in application 5, which is the most important one for you guys. And we'll actually be moving on to, well, I'll talk a little bit more about series, and then we'll move on to something else entirely next time. So again, thank you for your patience and sticking around with me later than usual. We will wrap up there. I'll post the video as usual with the notes where you can actually practice this other stuff. Thank you for your attention so far. Thank you for your participation. So we will wrap up there. Hopefully that was fine. Didn't say anything too crazy, but go over your notes, practice the problems, and let me know if you have questions next time. Until then, Have a good night, everyone. Have a good rest. Thank you once again for bearing with me, and sorry for the inconvenience. I will see you guys in the next one. Fill out the doodle poll. Let me know when I can schedule that next meeting. Ciao.